Hi, welcome to this next video about linear transformations and the relation to matrices. So we're going to look at two examples of linear transformations, namely rotations and reflections. We're going to describe them using matrices. But first let's see what's this relation between transformations and matrices. So linear transformations are transformations that behave in a linear way. So let's say L is a transformation. That means it maps from R2 to R2 in our case. Of course, you can also look at higher dimensional examples, but for us now it's all planar. And it's linear if it behaves like this. The sum of two vectors is mapped to the image, the sum of the images, like this. And if I have a scalar multiple of a vector, so let's say C times a vector V, it maps to the same scalar times the image of V. So this is a linear transformation. And for example, rotation observes this property. Because if I have a vector and well, let's say this vector, if I rotate it, it will go to some other point here on the unit circle that is now drawn. But if I have a multiple of it, definitely after rotation it will go to the multiple of that vector on the unit sphere. So the second one is easy to check. But also if I have the sum of two vectors, say first like that and then like that, if I just rotate these two vectors independently, the sum of those two vectors after rotation will end up exactly where the rotated sum has ended up. So these rules, I don't prove them very precisely like this, but I hope you agree with me. It's a linear transformation. Now, one of these consequences of these rules is that if I have a vector x, y, like this, well, what happens with it if I decompose it? It's actually, with respect to a basis, it's L of x times the first basis vector plus y times the second basis vector. And if I use these rules now, then I can conclude that it's x times L applied to the basis vector, the first one, and y times L applied to the second basis vector. So basically what the transformation does is all fixed by what it does with the unit vectors. Now if you have a matrix, say matrix M, we can make a linear transformation with that, because if I map x, y to M times xy, this will be linear. Let's say it has the shape A, B, C, D, like this. And now if I look in more detail at what happens here, it would be A, B, C, D times x, y. And you can have a similar decomposition that we have over there. So we would get A, B, C, D times x times first basis vector plus y times the second basis vector. And then, well, using linearity of matrix multiplication, you get that it's x times, well, and this one selects the first column, AC, and that one, multiplication here, I missed out one bracket, is y times, and this vector selects the second column, B times D. So similarly, this matrix multiplication as a linear transformation is if you know the first column and the second column, they sort of fix the transformation. And if you compare these two, then if I want to make a matrix that sort of fits with a linear transformation, I just need to know what the linear transformation does with the first basis vector. That will be my first column, and what it does with the second unit vector, the second base vector, will be the second column. All right, so now that we know this, we can apply it in the case of rotation of an angle theta. So let's see what happens with, that's denoted by r sub theta. What happens with the first basis vector? Well, this is sort of the standard situation. I take it here, I rotate it by theta, and of course we know the coordinates here to be cosine of theta, comma, the sine of theta. So let's write it here as a column vector, like this. Great. Okay, what happens with the other basis vector, 0, 1? Well, we can make our lives a bit easy. It's here. It will rotate by the same angle. It will be here. And then this angle, of course, will still be perpendicular, a right angle, because rotation maintains angles. So this will be the same coordinates, but shuffled a little bit, in the sense that we get minus the sine of theta, comma, the cosine of theta. There you go. So let's write that here as a column vector. It will be minus the sine of theta, cosine of theta. And altogether, from this we can take our rotation matrix, which is actually quite famous. And it's this. It's the cosine of theta, sine of theta, minus the sine of theta, cosine of theta. There you go. And maybe for yourself, you can, try out what happens if you put in theta is 90 degrees, or pi over 2, and see what comes out, what sort of matrices you get in concrete situations. But we'll not get into it because we have to move on and find this matrix for reflection. So where shall I put it on my blackboard? Maybe I have a nice corner here. So I'll denote it by S. And let's see what happens if we reflect in a line under an angle of theta over 2. The theta over 2 we choose because then we get very nice answers. So I put theta over 2 here. And what happens with the first basis vector? Well, the funny thing is that if I take any point here, with the unit vector, if I take this unit vector here, if I reflect it in this line, it will have the same effect as rotating it. I'm making this rotation image because that's what happens for this point, right? It's just really a rotation under an angle theta. So it ends up at exactly the same point as it does on the rotation. So it's again cosine of theta, sine of theta. So somewhere over here. Yeah. And let's see. Now we have to find out what happens with 0, 1. 0, 1. It's somewhere here. Now you can sort of guess where does it go? Somewhere over here, right? Somewhere over here. But there's another nice feature that again reflection also maintains the angle. So I know this is again a right angle, and I can use that to find the coordinates of this one, because again it has to be perpendicular to this one. Now here you had the one perpendicular vector, and the other one is another shuffle with a minus sign. So it is the one that we didn't have yet. So I can shuffle them, and now we get the minus in front of the cosine, right? So like this. That's our vector here. And with that, we find also a beautiful matrix for reflection in the line under an angle theta over 2 with the, the positive x-axis. And it's pretty similar to that one. It's cosine of theta, sine of theta, and then sine of theta minus the cosine of theta. So there you go. So any this sort of operations are done by very nice matrices. And just, of course, you can use this for your, if you want to make geometric programming and projections and rotations for 3D things. Even though this two-dimensional, if you make rotations in 3 dimensions, you just leave one coordinate invariant. So this quite easily extends to 3-dimensional rotations. But that's not the last thing I want to do. As a final thing, I want to show how if you compose 2 linear transformations, in the setting of matrices, this translates to multiplying these matrices. So suppose I'm interested in first rotating by an angle of theta, and then rotating by an angle of say psi, then if I want to find a matrix for this, I can find it by simply multiplying. And well, I'm going to do that and hopefully make no mistakes. So there you go, cosine of theta, sine of theta, I'm just filling it in, and then here minus the sine of theta, cosine of theta, times itself, cosine of, but then with an angle of psi. And there is the sine minus the sine, the cosine. There you go. And a multiplication of matrices, well, I hope you've seen a video about this or simply know. You multiply the first line with the first row with the first column, so we get cosine of theta times the cosine of phi. And then, I'm going to be short of space here for sure, minus the sine of theta times the sine of phi. So maybe I'm not going to do the whole matrix. You know how it goes. From here you can do the other multiplications. But the point is, why this could be interesting is the following. Because I know this is a linear transformation, and rotating first an angle of phi and then rotating under an angle theta should be the same as rotating over the sum angle. And this gives you an interesting result, because if I write out what this is, it's the cosine of theta plus phi, like that, and then we can do the rest of the matrix, but I'm mostly interested in that top one. Minus the sine theta plus phi, cosine theta plus phi, like that. There you go. And what we get from this little computation is one of the sum formulas for from trigonometry, the ones that we always so dislike because they look so complicated and they're easy to forget. But actually, once you know this and you know this formula, this gives you a beautiful way to derive them whenever you need them, because we can see that the cosine of theta plus phi is equal to this one. And of course, if you would have expanded the other entries here, you would have found similar formulas for sine of this sum, etc. Here the bracket misses. So there's some application there, and it's also good to know about this multiplication property for composition of transformations. So that's about it. And I think it's beautiful how geometric features are represented in a numerical algebraic way like this in matrices. So I hope you enjoy that too.